In 25.7, we're going to take a look at goodness of fit tests, and we're going to consider the case of one-way classifications. If we have some sort of assertion regarding the way in which we expect a distribution to play out, then we can make assertions and test whether or not it the data is coming in consistent with our expectations. In a one-way classification hypothesis test, our null hypothesis will be that we have certain we can correctly make certain statements about the probability in each category against the alternative hypothesis HA that the null hypothesis is not true or the null hypothesis is false. We must again identify a level of significance, and then we need to look at the expected frequency of a data set compared to the observed frequency. You can think of this as, suppose you rolled a dice 1,000 times and you counted the number of times you rolled a 1, a 2, a 3, a 4, a 5, or 6. You know how to calculate the expected number. If you had 1,000 rolls of the dice, then you would take 1,000 times 1/6, and you would have the expected number of observations that you would get from throwing the dice. The test statistic is calculated in one of two ways, and then compared to the critical values of what's called the chi-squared distribution. The chi-squared test statistic is calculated as the observed number that came out in each category minus the expected number squared divided by the expected number, and that's the and sum those over all the different categories in which you have made observations, and that'll give you your chi-squared value in your test statistic. And you're going to compare it against critical values to decide whether to accept the null hypothesis or reject the null hypothesis. In order to apply this test, you're going to need to look up these critical values of the chi-squared distribution in order to come up with what you need in order to make a hypothesis test of this type. The chi-squared distribution, it's important to look at, is basically looking at a bunch of potential errors in different observations and then squaring each of those errors. And because we're squaring the errors, there's no possibility of a negative value. So the chi-squared distribution always is bounded on the left by 0, because you can't sum up the square of a bunch of error and ever get a negative value. It's always going to be positive. The number of degrees of freedom influences the shape of the chi-squared distribution. Again, notice all of these are bounded on the left by 0, because you can't possibly have a value that comes out less than 0. And the larger the number of degrees of freedom, the more it looks closer to a normal distribution, a bell-shaped curve. When degrees of freedom gets higher, it gets closer to that bell-shaped curve. We'll often need to look up these critical values, and usually we'll be dealing with critical values that are up on this end. So if you have the case of the dice that we talked about before, you're going to take the number of degrees of freedom equal to 6 minus 1, or 5, and decide what level of significance you're concerned with, and then you'll pick one of these critical values depending on the level of significance that you select for that. While we have this table up, one of the things I wanted to point out is that we we usually look at this upper tail, but occasionally people look at this lower tail. Sometimes when we have agreement with agreement that is so consistent with expected values that it makes us suspicious, and this in fact can be used. This test can actually be used not just to tell when something is inconsistent with expectations, but you can also tell when things are so consistent with expectations that we suspect something funny might have gone on. So this test can also be used and has been used to catch people who have made up data that just fits too well expected outcomes. Those are the continuation of the chi-squared distribution table, just with larger degrees of freedom numbers here. If we need to make a conduct a hypothesis test where we are testing distribution assumptions, such as we think these are normally distributed, we think these are distributed according to the Poisson distribution or the exponential distribution or the log normal distribution or any other distribution, we can use the chi-squared goodness of fit test for such an application. The chi-squared goodness of fit test ends up being used in a wide variety of different applications. We have some new issues that we haven't had in some of our previous hypothesis tests that are unique to the chi-squared test. Sometimes we need to estimate parameters of our distribution. Sometimes we say we're going to test whether or not this is a normal distribution, and in order to decide whether it's a normal distribution, you'll have to make some categories associated with what should be expected. To do that, you're going to need to use you're going to need a mean value, and you're going to need a standard deviation, and those are going to come from your sample usually, in which case you'll be estimating those parameters. This is probably easiest to see in application, and I do have some cases involving this type of chi-squared test. The second issue in the chi-squared test that I wanted to bring up is that if you have small categories or sometimes small cells in which you're expecting fewer than 5 observations, that cell size is too small and you need to combine some in order to get a reasonable test. Thus, when we're looking at a distribution that has some tails to it, we're often going to have to increase the categories when we're in the tails so that we can keep our expected number above 5, at 5 or more, in order to conduct the chi-square test in a reasonable way. Sometimes when we do this when we're doing this type of hypothesis test to see if a particular type of distribution applies, we'll sometimes need to make estimates of a parameter of the distribution. And here I've got some different examples of hypotheses that require no estimation of a parameter. Then I have another set of hypotheses that do require an estimation of a parameter. I'll start with the ones that we don't make any estimate of a parameter. Yeah, our null hypothesis might be the process is distributed according to the Poisson distribution with lambda equals 14.2. Thus, we made the value of lambda part of the null hypothesis. In the next example of one of these hypotheses that requires no estimation of parameters, we might make the assertion that a hypothesis is described by a normal distribution with a mean of 13 and a standard deviation of 1.4. We also have the special case of a uniform distribution which doesn't have any parameter, in which case our null hypothesis is just that we believe the data is uniformly distributed. Hypothesis tests that require the estimation of a parameter might include this process described by a Poisson distribution, but we haven't decided what we haven't asserted what we believe lambda to be. The next hypothesis that requires an estimation of parameter is a null hypothesis that simply says we believe that this process is described by a normal distribution. You won't know what kind of normal distribution until you start using the sample mean and sample standard deviation. Then the last example I have of one of these hypotheses that requires the estimation of parameter is if your null hypothesis is that the process is described by a normal distribution with a mean of 13. Now that means that we've embedded one of the parameters into the null hypothesis, but we haven't made any assertion about the variance or standard deviation, which means we're going to have to get that from the sample that we collect and use the sample standard deviation to estimate the population standard deviation. The last section that I want to deal with in Chapter 25 is I wanted to mention that there is a section on non-parametric tests, and we're not going to go into it very heavily. When we have a distribution that is distinctly not normal, we must rely on alternative hypothesis test methods and alternative confidence interval methods. We can't use the methods that we've been studying so far in this chapter. For example, instead of